Thank you, Marcus, and thanks to the organisers. It's a pleasure to be here. Very grateful to be at this old historic institute. As Marcus mentioned, we've pulled the bait and switch, so I'll be presenting Franz's slides. And I guess the aim of this talk is to give a very basic introduction to time frequency analysis, quantum harmonic analysis, and where the two meet and push each other forward. So parts of this talk will probably be very basic for the audience, but hopefully if there's an area you're less familiar with, we'll at least touch on it in this talk and go a bit deeper in the talks to follow. So we'll start by introducing the building blocks of time frequency analysis. So the goal of time frequency analysis is a joint representation in both the time and frequency plane. And the building blocks are really the time frequency shifts. So we have the pi time frequency shifts, which are simply a composition of a translation and a modulation operator. And perhaps more familiar in the physics community, the Heisenberg-Weyl operators, or the symmetric time frequency shifts in the time frequency community, just include this phase factor. So both pi and rho are projective unitary representations of phase space, which just means that we have this composition where we introduce a phase factor upon composing two of them. So most of our time frequency results will be stated in terms of the pi shifts, but when we go to quantum harmonic analysis, because that's based on the Weyl quantization, it's often more natural to use the Heisenberg-Weyl operators, especially later on if you look at metaplectic operators and such. So with our two time frequency shifts, we can introduce the short time Fourier transform and the ambiguity function. So we can intuit the short time Fourier transform. We first consider G, our atom or our window, to be an indicator function. Then we're really just sliding a window along time and taking the Fourier transform of F in that window. And later on, we'll see that we don't really want to take an indicator function. We want to take a nicer window, but I'll get to that. And another way of thinking about this is if we take our window or our atom, we're translating this around the time frequency plane and then projecting F onto that. Now, similarly, if we do this with rho, we arrive at the ambiguity function or the cross-ambiguity function. I'll talk about the ambiguity function and the Wigner distribution almost always in terms of two separate functions. So for the most part, I'll drop the cross. And these are, of course, connected by a phase factor, just like our time frequency and our Heisenberg-Weyl operators were connected by a phase factor. Now, one very nice feature of the STFT is what's known as Moyle's identity, or the orthogonality conditions. So if we take four functions in L2, if we take what is the inner product on L2 of R2 of the two STFTs with respect to each other, this just amounts to the inner product of the arguments and the windows of the two STFTs. Okay, so if we have two orthogonal windows, this obviously reduces to 0, and two orthogonal arguments reduces to 0. Now, if we consider Moyle's identity in a weak sense, then we can reconstruct any f in L2 with respect to a normalized G. And in fact, in this equation, if we instead of taking G and G in the window and the reconstruction, we can take any two non-orthogonal atoms there and just introduce an inner product. Now, because the ambiguity function, and in fact later the Wigner distribution, are connected to the STFT via a unitary transform, the same orthogonality conditions hold for both the ambiguity function, the Wigner distribution, and in fact any metaplectic time frequency distribution. And one implication of this is that for normalized G, the STFT is an isometry into L2 of phase space. If we consider the image of that isometry, then we have what's called Gabor space. So we just consider the image of all of L2 of R under Vg for some fixed G. And this is going to be not only a subspace of L2 R2, but in fact a reproducing kernel Hilbert space. Okay, so this means that evaluation at each point is bounded uniformly, and we can simply take the inner product with this reproducing kernel to get any function. So the function now f is the image of the function capital F is the image of some little f with respect to the STFT, and that is then in the reproducing kernel Hilbert space. And a nice way to express that, especially when we go on to atomic decompositions and co-orbit theory, is in terms of this twisted convolution product. So the twisted convolution, similar to the regular convolution, but we include a phase factor of the cocycle. And then our VGG with that cocycle becomes the kernel of our reproducing kernel Hilbert space. So any VG of F, twisted convolution with VGG, again gives VGF. So far, I've introduced the STFT and the ambiguity function as possible ways to give a representation of a function in the time frequency space. But there's a plethora of options we could choose from. We'll see closely related to the ambiguity function is the Wigner distribution. And this will become very important. You don't need to remember the formula, but the concept will become important later on when we go to quantum harmonic analysis. If we were to take W of F and F, then this becomes a quadratic time frequency distribution. Another example of that is the spectrogram. So if we just take the modulus squared of the STFT or the ambiguity function, and we find the spectrogram. And this is in fact of Cohen's class form, which is simply some temper distribution convolved with the Wigner function, or Wigner distribution of the function. And now when we go to time frequency analysis, we're working on R2D, or R2 for this talk. So instead of the standard Fourier transform, it becomes a lot more natural to use the symplectic Fourier transform. This is just the Fourier transform now with respect to the symplectic form instead of the dot product. And this carries pretty much all of the nice features we want from the Fourier transform. It's unitary, we can extend it to L2. And one nice feature is that it's own inverse. So taking the symplectic Fourier of the symplectic Fourier gives us our original function and L1 function. And with that introduced, we can note that by taking the symplectic Fourier transform of the Wigner distribution, we get the ambiguity function. And because it's its own inverse, we can also take the symplectic Fourier transform of the ambiguity function, and that gives us the Wigner distribution. Some very interesting operators in time frequency analysis are the localization operators. If we interpret the STFT as the representation of the time frequency concentration of our function f, and what a localization operator tries to do is to reconstruct that perhaps based on a subset of all of phase space or a weighted distribution on that. So the localization operator simply takes the STFT of f and then reconstructs it with respect to this weight a. Okay, so initially we'll just consider a to be some bounded function. If we consider that to be an indicator function, then like I said, this is reconstructing f based on its time frequency concentration in this subset of time frequency space. We'll consider a much larger range of masks in this talk. If we take a specifically nice window, so the Gaussian, for example, or the Gaussian, then we can identify Gabor space with respect to the Gaussian window with the Bargmann-Fock space. Okay, so if we identify time frequency space with the complex plane, then our Gabor space with respect to the Gaussian becomes the Bargmann-Fock space. I don't think they're defined in this slide deck, but the modulation spaces are functions which have an STFT and a weighted Lebesgue space. I won't go too deep into that now. But these modulation spaces can then also be identified with the P Bargmann-Fock spaces. Now I'll move on to the quantum harmonic side of things. For quantum harmonic analysis, we want to reproduce the kind of building blocks from harmonic analysis. So we want our family of Lebesgue spaces,
our family of Banach spaces, which in the classical picture are Lebesgue spaces. We want our translations, our Fourier transforms. So I'll kind of go by item and try and define these things. So the analog for the Lebesgue spaces, which we'll work with in QHA, are going to be our Schatten classes. We define our Schatten P class in the following manner. So obviously, for P equals 1, these are the trace class operators, so all operators for which the trace is finite. The trace can be taken with respect to any O and B. And a particularly important instance is going to be the Hilbert-Schmidt operators. So a Schatten P class of P equals 2, just like in the L2 case, this becomes a Hilbert space. And our inner product is just given by the trace of ST star. Okay, so the inner product of S and T Hilbert-Schmidt operators is the trace of ST star. And we can kind of think of these Schatten classes as the operators for which the singular values are in a little LP sequence space. With that, we can introduce, without justification yet, the translation of an operator. So we can do this in terms of either the pi shifts or the rho shifts, because they just are equivalent to a phase factor, which is going to cancel out. So the translation of an operator S is just the composition of S pi Z star. The eigenvalues. Eigenvalues here, yeah. So once we have a translation of operators, we can start to build our convolutions. For convolutions, and indeed for most of quantum harmonic analysis, our trace is going to play the role of our integral in classical harmonic analysis. If we think of how the convolutions are defined in terms of integrals, we replace the integrals with traces, the translations of functions with translations of operators. We get the following notions. So initially, we consider two trace class operators, S and T, and some L1 function F. We can define both a convolution, an operator-operator convolution and an operator-function convolution. So for an operator-operator convolution, this is going to define a function on phase space. And this is just given by the inner product, or the trace of S composed with translations of T. Our T hat here is just composing with the parity operator to get this, this flip of the Weil symbol. Okay, so in the rank 1 case, we can take F tensor F, involve this with G tensor G, and this is going to give us our spectrogram. Now, if we take an L1 function and a trace class operator, we can also define a function operator convolution. The capital F here is just a function. And here again, we're going to use our translation of operators as our translation of functions. And our function operator convolution then defines an operator. So for L1 and S1, we can consider this as a Bochner integral. More generally, we can consider this integral weakly. Now again, if we consider the rank 1 case, so we'll take some L1 function A, some G tensor H, then this gives us exactly our localization operator with the mask A and the windows G and H. Already we're seeing this kind of interplay between quantum harmonic analysis and time frequency analysis, which will be a theme of this. And I've introduced the translation of an operator without really motivating it. But to do that, we'll consider what's called the Weil quantization. So a quantization scheme, just a way of associating a function on phase space to an operator. And often in time frequency analysis, this is considered weakly in the following sense. So if we have some distribution A, then the Weyl quantization of A acting on some function f, inner product G, this is going to be the inner product now on phase space of A with the Wigner distribution of Fg. Okay, so it is quite a common interpretation of time frequency analysis, but perhaps a more intuitive way is that the symbol corresponding to the rank 1 operator, G tensor F, is just going to be the Wigner distribution of GF. Now, for any continuous map from the Schwartz space to temper distributions, there exists some distribution corresponding to that operator, the Weyl quantization. So we talk about LA being the Weyl quantization of the symbol A, and we can also talk about A being the Weyl symbol of that operator. And with that quantization defined, then our translation of operators simply becomes the translation on the Weyl symbol level. Okay, so if we translate an operator S and look at its Weyl symbol, that Weyl symbol is just the translation of the Weyl symbol of S. Similarly, the convolutions become convolutions on the Weyl symbol level. So an operator-operator convolution, remember that gives a function, and that function given by the convolution of Weyl symbols. And if we look at the Weyl symbol of the function-operator convolution, this is the convolution of the function with the Weyl symbol of the operator. For example, the Weyl transform is just given by the convolution with the parity operator, with a factor of 2, and the Wigner transform, the Wigner distribution rather, is given by the operator-operator convolution. And it's perhaps easier to think when you see this that, okay, but then QHA is just going to be moving things to the Weyl symbol level, doing things there, vice versa. And the intricacy comes because the Schatten classes don't map onto the L1 classes. So we do have that for L2. So L2 symbols correspond to Hilbert-Schmidt operators, but there's no nice correspondence between trace class operators and their symbols or L1 functions and their operators. A lot of the more intricate questions in quantum harmonic analysis are related to trace class operators or general P for P not equal to 2. So in the function case, we know that we have the Young's inequality. So given P and Q satisfying this Young's relation, if we take F in LP, G in LQ, then their convolution is going to live in this LR space. So similarly, if we go to the operators, now we have to be a bit careful because we have Lebesgue and Schatten classes, but it turns out that indeed, if we take A in LP, S in LP, and T in SQ, then both the function operator and operator-operator convolution respect this Young type inequality. So again, if we take P and Q to be 2 here, then we have this direct kind of translation onto the Weyl symbol in L2. That all follows nicely, but to extend that to general Schatten classes, there's a bit more work involved. Now for any operator, we've talked about the Weyl symbol, but another way we can associate a function to that is via the spreading representation. So the so-called spreading representation, simply because it's in some sense a measure of how much the operator spreads a function in time frequency. If we imagine that this is just a direct delta at the origin, then this is just the identity. Every operator has a corresponding spreading function, and then we can reconstruct the operator as this weighted integral of time frequency shifts on phase space. Now we've defined translations and convolutions. Maybe the next natural step for harmonic analysis world building is the Fourier transform. And for that, we'll introduce what's called the Fourier-Wigner or the Fourier-Weyl transform. This is just given by, initially for a trace class operator, given by the trace of S composed with the Weyl-Heisenberg or a time frequency shift and with the phase factor. So in the rank 1 case, the Fourier-Wigner transform of f tends to g is the ambiguity function. And if we think back to when we introduced the symplectic Fourier transform, the symplectic Fourier transform of the ambiguity function is the Wigner distribution. Okay, so again, the Fourier-Wigner transform just gives us the symplectic Fourier transform of the Weil symbol, the operator. And this is closely related to the spreading representation. And in fact, if we define the spreading representation in terms of rho instead of pi, then we drop this phase factor. And just as in the function case, we have this convolution theorem. So taking we have to be a bit mindful of whether we're on operators or functions. If we take the symplectic Fourier transform of an operator-operator convolution, this is equivalent to the product of the Fourier-Wigner transforms of the two operators. If we take the Fourier-Wigner transform of a function-operator convolution, we get the product of the symplectic Fourier transform on the function or distribution and the Fourier-Wigner on the operator. Okay, so exactly what you would hope for in a convolution theorem, but something to keep in mind is the operator function distinction. So some nice facts about the Fourier-Wigner transform is that, like in the function case, this extends to a unitary mapping from the Hilbert-Schmidt operators to L2 of R2D. We have a Riemann-Lebesgue lemma. So if any trace class operator, we have that the Fourier-Wigner is in C0 on phase space. And we have this spreading type reconstruction. So here in terms of our row shifts, we take the Fourier-Wigner transform of any trace class operator, then we can essentially invert that operation by taking a spreading representation, a weighted integral of time frequency shifts back to FW. I guess the motivation behind this slide is everything that you would hope would be true based on the function case lifts to the Fourier-Wigner transform. Okay, so some more kind of classical harmonic analysis results, which it turns out does extend to QHA. First of all, we have Wiener's approximation theorem. So again, we have this for different p-values. For p equals 2, then we can just, again, reduce things to the Weil symbol, use our Wiener's approximation theorem there. But more interestingly, we can actually do the same thing for trace class operators. So if the Fourier-Wigner of our operator is nowhere 0, then the translates of the operator are in fact dense in the trace class. And vice versa. If we have the translates are dense, then the Fourier-Wigner of our operator is nowhere 0. Now for the rank 1 operator, this is a question about localization operators. That connection might not be immediately clear here, but it does reduce to that. So this is a question of when the localization operators are dense in the trace class. This was discussed some years ago by Göchner and Bayer. And just as in the Wiener's approximation theorem, we can consider Wiener's Tauberian theorem and find an analog of that for operators in terms of the convolutions. Now for the STFT, we have Lieb's inequalities. So for values of p either between 1 and 2 or greater than 2, we have the two equivalent conditions. This is going to be closely related to the Fourier-Wigner transform of our operators. In particular, if we have the STFT of f with window G being essentially supported on some domain, so most of the time frequency content of f being contained in a small region of phase space, then that, well, not small after all, that region actually has to be of a certain size. This is essentially saying we can't find any function f concentrated on an arbitrarily small area of the phase space. So a classic uncertainty principle. Now if we use
Wigner, in introducing QHA, considered a Hausdorff-Young inequality for operators. As in the function case, we'll consider two P and Q exponential conjugates. And then for any S in TP, so P here in between trace class and Hilbert-Schmidt, any S in TP, this notation is inconsistent. T here should be S. So any Schatten class P, then the Fourier-Wigner of S is then in LQ. Okay, so a typical Hausdorff-Young inequality, but now with an operator Fourier transform. If we consider the rank 1 case again, recall that the Fourier-Wigner transform of a rank 1 is an ambiguity function. The modulus of the ambiguity function is equal to the STFT. So then we can consider the Hausdorff-Young from Wigner in this setting, and we simply get this inequality on the STFT. If we look at the right-hand side, we're missing a factor here. But if we consider as a consequence of that, for a trace class operator, we have this final inequality. And this is, perhaps I didn't mention it before, but the Schatten class norms are strictly decreasing. So the trace class norm is going to be larger than the SP norm for any P greater than 1. So if we combine those uncertainty principles, we can kind of find this essential support condition for the Fourier-Wigner. So we don't have to go too deep into all of these factors, but what this equation is getting at is if we want a very well concentrated Fourier-Wigner transform, okay, so if we want to find some operator maximally concentrated in some small region of phase space, then that's going to come at the cost of a large norm, a large trace class norm. Okay. So we've talked about a couple of quantization schemes. We have our Weyl quantization. We can quantize with respect to a localization operator. In fact, any operator R, bounded, of course, is going to define both a quantization scheme. Okay, so via operator function convolutions, we can use any bounded operator to send a function to an operator. And it's also going to define a time frequency distribution. So we can use an operator convolution with the rank 1, f tends to f, and that's going to send any f to a quadratic time frequency distribution. And in fact, that distribution is going to be of Cohen's class type, precisely because the operator convolution is just an operator of Weyl symbols. So this is going to reduce to a convolution with the Wigner distribution. Like I mentioned, we have two examples of that in Weyl quantization and localization operators. Then the corresponding time frequency distributions are the Wigner distribution and the spectrogram. The two convolutions are in some sense dual to each other. So in the last line, if we take the operator function convolution acting on a function, then this is in a sense dual to the Weyl symbol, the distribution in a product with the Cohen's class with respect to that operator. In the rank 1 case, we saw that an operator function convolution gives a localization operator. If we generalize that to higher rank operators, then we recover the notion of a mixed state localization operator. Okay, so if we think of the rank 1 as being a pure state localization operator, then extending to an arbitrary rank is going to give us our mixed state localization operators. And this is, you can equally think of this as being a multi-window localization operator. So localization with some mask, then with respect to multiple windows, analysis and reconstruction. And if we then consider the inner product of that resulting operator as in the previous slide, so now we'll take some indicator function on omega. The inner product of that operator acting on a function with the function itself is then going to be the integral of the Cohen's class over that domain. So for the rank 1 case, this is just going to be the integral of the spectrogram over some domain. And accordingly, if we want to find the functions which maximize the time frequency concentration with respect to that Cohen's class in the domain, then that's going to lead us to the eigenfunctions of the mixed state localization operator. So just as if we want to maximize the spectrogram in some domain, we look at the eigenfunctions of the localization operator. Now we're just lifting that to an arbitrary rank. So now we'll move, in some sense, from functions to operators and ask ourselves, what might time frequency concepts look like on the level of operators? So far, we've seen time frequency concepts arising in QHA, but this is really due to the quantization. We're still only looking at translations. When we see these STFTs and the like arising, this is happening because of our viral quantization, which we're building QHA on. So now we try and ask, what would time frequency concepts look like on operators as opposed to just harmonic analysis? If we have some function in L2, there are a couple of ways that we can associate that with an operator. We can take the rank 1 tensor product, F tensor F, or we could take some fixed E and take the tensor product with that. So if we're considering now a collection of functions, we call this D because later on this is going to be our data set. We can take some orthonormal system of the same number of elements as our data set. Then we can either construct what we call the data operator. So SD is just going to be the tensor products of our data points with some element in our orthonormal system. Or we can consider SD star, so this is the covariance operator, and this is just the sum over our rank 1 tensor products. Then define the operator STFT in the following way. So given two operators, we'll start with them being Hilbert-Schmidt. Our operator STFT is going to be a function on phase space, operator valued. So for every Z in phase space, we find what turns out to be a trace class operator. The operator STFT is defined S star pi Z star of T. And if we plug in our two different kind of interpretations of an operator, we can see why this might be called the operator STFT. For a rank 1 operator, we just get the STFT of F with respect to some window G with some rank 1 operator. More generally, if we have our operators S and T with our FNs as the data points that we're interested in, we take the operator STFT, we find a sum over the STFTs of our functions, and these are, in some sense, weights for our rank 1 operators in the operator sense. So again, the operator STFT is a trace class valued function on phase space. The weights for each of these rank 1 operators is given by the STFT. This is closely related to the total correlation function. So the total correlation function, so-called because it identifies all correlations within a data set, looks at the pointwise sum of the STFTs or spectrograms.
Turns out that if we take the Hilbert-Schmidt norm of the operator STFT at any point, this is going to give us the total correlation function at that point. Our operator STFT, in some sense, captures the correlations of our data sets, but it also has this structure in the operator sense of telling us where in the data set those correlations occur. And I'm not sure if it touched on it here, but if we again look at the symbol level, if we take the Fourier-Wigner transform of the operator STFT, we end up with up to some change of coordinates an STFT on the Weyl symbols. So the basic properties of the operator STFT mirror the basic properties of the STFT. It's now an isometry from Hilbert-Schmidt operators to L2 Hilbert-Schmidt valued. We have this Moyal's type identity. If we take the inner product on L2 Hilbert-Schmidt valued, then we get the inner product of our windows and our arguments in Hilbert-Schmidt space. Now, just like our Gabor space was a reproducing kernel Hilbert space, our operator Gabor space is a reproducing kernel or vector valued reproducing kernel Hilbert space. Now, instead of our evaluation being given by some inner product, our evaluation is given by these operators, but with that accounted for, we have this same reproducing kernel structure. And just like in the function case, that reproducing kernel structure can then be used to go on and define atomic decompositions and frames for the operator STFT. I've kind of mentioned this interpretation of our operator representing a data set. One concrete example of quantum harmonic analysis in data analysis is if we were to consider the time frequency augmentation of a data set. By time frequency augmentation, we mean adding to our data set small perturbations of the data points in the time frequency setting. So for every Fi, we also include these time frequency translations of Fi for some small domain. We then build up our, perhaps bad notation, but build up our covariance operators for this augmented data set. Okay, so we augment our data points and consider the covariance operator associated to that. This turns out to be a mixed state localization operator. Okay, so this is equivalent to convolving our original covariance operator with the indicator function on the domain that we're augmenting the data set by. I'm not sure if it's in these slides, but you can actually use this fact to prove what's empirically known, that augmenting a data set actually leads to the smoothing of the principal components or the eigenfunctions of the covariance operator. Another perspective on QHA, for if they're in the audience, but recently there's been some very interesting work done on Wigner kernels. So analyzing an operator via its Wigner kernel, and by that I mean the following procedure. If we have some operator T, we're interested in analyzing this, then we consider the action of T in the following sense. We take two functions, and we consider the tensor product of T of F with T of G. Okay, so we're interested in examining T. We consider the tensor product of T of F and T of G. Now this is then related to a kernel acting on F tensor G. We can write T of F tensor T of G is equal to some kernel K of T acting on F tensor G. But in the quantum harmonic sense, what we can do is move this to the Fourier-Wigner side. If we do so, then we find that this Wigner kernel procedure actually just amounts to finding the Fourier-Wigner multiplier of the operator. Okay, so there's some linear operator K satisfying that
that kernel condition for T, it turns out that K is precisely the Fourier-Wigner multiplier for T. In that sense, the Wigner kernel analysis of an operator is really just considering the Fourier multiplier for that operator. Now moving on to Gabor frames. If any very nicely behaved G, here we've said that it's in the Falkning algebra without defining that, then we say that the system pi lambda of G, so we're looking at time frequency shifts of G with respect to some lattice lambda, is going to generate a Gabor frame if there are finite constants satisfying this frame condition. So we can think of a frame as kind of extending the notion of an orthonormal basis, relaxing it a little. And to every Gabor system, we can associate the Gabor frame operator. So in the first step, the inner product, we analyze the function with respect to our window, and then reconstruct our function by taking the sum. So I guess the intuition here is that this is in some sense a discretization of the function reconstruction from the STFT. But while for the STFT we can do that for any window, in the frame setting this becomes a much more delicate question. So if we define the frame operator in that manner, then we can define the canonical dual frame for some window G by taking the inverse of the frame operator. Then we have the final two reconstruction formulas. And from a quantum harmonic perspective, this really amounts to a periodicity problem. So we talked about, we defined the Gabor frames in terms of one window, but now we define the operators with arbitrary rank. So we say that an operator, a bounded linear operator from Falkning operators to Mauer distributions, is translation invariant or invariant with respect to some lattice if T commutes with every time frequency shift on that lattice. If we rewrite that equation, this is essentially saying that translation of an operator by any point on that lattice, again, gives us the operator. We can then consider the periodization of an operator as the sum over all its translations. And these can be thought of as periodic operators. The key observation here, made by Falkning and Kozak, was that Gabor frame operators are the rank 1 periodizations. The Gabor frame operators translate with time frequency shifts on the adjoint lattice that they're defined on. Now, in QHA, just as periodic functions can be expanded, we can then look at periodic operator expansions in the Fourier-Wigner setting. And again, the dual lattice notion is going to be replaced by the adjoint lattice. So the adjoint lattice is essentially the dual lattice, but now taking into account this symplectic form. So the Poisson summation for operators, which is going to give us most of our frame results, is simply the well-known Poisson summation, but now we're looking at translations of the operator and the Fourier-Wigner of the operator. This should have a T here, so the Fourier-Wigner of T evaluated on the adjoint lattice, and then the translations about Heisenberg-Weyl operators. Okay, and this is actually going to give us the Janssen's representation of the operator. So on the previous slide here, if we consider T now to be a rank 1 operator, recall that the Fourier-Wigner of that is the ambiguity function.
Then directly plugging that into our Poisson summation formula, we get the Janssen's representation for a Gabor frame. So we'll come back to that in a moment, but before that, we'll introduce the notion of a Gabor G frame now. So we've thought about frames acting on functions. I think, here we are, we formulate that in functions. So a Gabor G frame is an extension of the concept of a frame. Now, instead of just looking at the inner product between the frame and our function of interest, we consider some general operator acting on that function. So we ask for the same frame bounds, A and B, but now we just have translations of some operator acting on F. And obviously, for rank 1 operator, this is going to give us precisely the Gabor frame condition. Just like we associate the Gabor frame operator to some frame system, for a Gabor G frame, we consider the Gabor G frame operator. So this looks familiar. This is just the periodization of our operator F star S. So the condition that S forms a Gabor G frame is essentially the condition that this operator is bounded and invertible. Just like we have dual frames in the function setting, we can consider dual G frames in the G frame setting. So there's going to be two operators such that the Gabor G frame operator of S and T is going to give us the identity. Accordingly, we can consider the Wessler-Rachs condition, and that's then just given by the Fourier-Wigner of S star T evaluated at the identity, or rather only being evaluated the identity. Skottenland went on to show the existence. And this essentially relies on a von Neumann argument around this expansion. A little pressed for time now, so I'll have to rush a little bit through these. So far we've considered translations of operators, but to lift to time frequency analysis for operators, we want to introduce a modulation as well. So this was first studied by Berger and Fulcher. And just like a translation amounts to a translation of the Weil symbol, our modulation is going to result in a modulation of the Weil symbol. Equivalently, if you look at the Fourier-Wigner side, a modulation of an operator is a translation of the Fourier-Wigner of the operator. With both a translation and a modulation in hand, we can go on to define what we call time frequency for quantum time frequency analysis. So our time frequency shifts are going to be replaced by our gamma shifts, which amount to a translation and a modulation with some change of variables. And our observation is that the effect that this has on the Weil symbol of an operator is essentially a time frequency shift with this change of variables. So this change of variables might look familiar to those that have investigated mapping properties for Weil symbols. It's essentially a 45-degree rotation with some symplectic action on the second half. Now, if we consider the inner product with respect to our gamma shifts, we arrive at the polarized Cohen's class. So this is now for each operator, we'll fix on window S, and then for any operator T which we analyze, we're going to find a function on double phase space, or R4D. The rank 1 case, this is just going to be the product of our STFTs. And this gives rise to the concept of a bi-localization operator in the rank 1 case. And if we discretize the polarized Cohen's class with respect to some rank 1 GG, then this is just the Gabor matrix of our operator. Like I mentioned before, if we take the Fourier-Wigner transform of our operator STFT, then up to some change of variables, we land on our polarized Cohen's class. Just like the function case, we have our Moyal's identity or orthogonality conditions operators in HS. Now we also have our reproducing property. So we have the notion of a twisted convolution given here. And with that, we can consider the image of our polarized Cohen's class is going to be a reproducing kernel Hilbert subspace of L2 R4D. And indeed, for the rank 1 case, this reproducing property is being used in the physics literature to look at decay of operators or decay of states. And finally, in quantum time frequency analysis, we have this analog to the Faltinger algebra, and that's given by the Faltinger operators. Okay, so these are precisely the operators with Weil symbols in the Faltinger algebra. Or alternatively, we can define these operators as those T such that QTT is in L1. These operators can also be described as the nuclear operators. So this is a trace type condition for rank 1 operators from M infinity to M1. And finally, if we plug all this in the rank 1 case, we land on this magic identity for the study of pseudo-differential operators. This identity, which underpins a lot of the mapping properties for localization operators, is just given by this form. So I think I'm just out of time. Here are some partially out-of-date references for the talk, and thank you for your time.